So now we will begin with the design of R.C.C cantilever retaining wall. Whatever we have learned till this lecture, we will be using that or applying that to study the design. So this is a picture showing a cantilever retaining wall under construction. This is the stem and this is the toe slab. The heel slab is on the back side. This part we have covered in the previous slide, that is the structural behavior of R.C.C cantilever retaining wall. I will be revising it quickly in the next slide. So the structural behavior of R.C.C cantilever retaining wall is such that all the individual components behave individually as cantilevers. So first is the stem fixed at this point and free at this point. The load acting on this cantilever portion is this lateral earth pressure. So it will bend like this as shown in red color, and the tension will be on this side. In the heel slab, the downward weight is the load acting on the heel slab, plus there is additionally upward soil pressure acting on this heel slab. So as this value will be more than this value, hence the resultant will be also downward. So the load on heel slab is resultant vertically downward load, and this is the fixed end and this is the free end, hence it deflects like this due to this downward load, and hence the tension is on the upper face. On the on the toe slab, there are two forces. One is the downward weight of this soil, this much soil, and second is the upward soil pressure. As this value is very less, we can neglect it. So the only force will be the upward force. So as the direction of load is upward, and this is the fixed end now and this is the free end, the toe slab will bend like this, leading to tension on the bottom side. So here in stem, tension is on the inner side, in heel slab on upper side, and on toe slab on the bottom side. So this should be clear to you. Now what is the design of R.C.C cantilever retaining wall? So as we have studied in the previous R.C.C subject and for previous other components of R.C.C like footing or beam or column or slab, R.C.C design basically means two things, that is the selection of dimensions of the R.C.C component, and second is the provision of reinforcement in the R.C.C component. So similarly, for the design of R.C.C cantilever retaining wall, we have to follow two major steps. That is, first we need to select the dimensions of the different components of cantilever retaining wall. Like if this is the retaining wall, you have to decide that what will be the thickness of this stem, what will be the thickness of this slab, what will be the total width of this slab, etc. So all this comes under first part, and the second part is when you have decided the dimensions, then we will provide the reinforcements in different components of retaining wall according to their structural behavior or action. So there are two basic parts. First is assumption of dimensions of retaining wall. First we assume all these dimensions as I have shown you, and then after we have all these dimensions, we apply stability checks, which I have already explained to you in the previous lecture. After the stability checks are true or okay, then we provide reinforcement, that is we design the reinforcement and draw the detailing of all the different types of reinforcements in all the different components. So we will do this in detail in the coming slides. You have to decide the dimensions of stem, that is thickness of stem here and here, the dimensions of base slab, that is its width and its thickness, etc. So the base width of base slab B is assumed to be 0.5 to 0.6 h. So we have calculated this h. This is the base parameter on the basis of which every dimension will be decided. So B will be between 0.4 to 0.6 h. So students, note here that many books, different books have used these formulas differently. So in some of the books you may find these formulas to be slightly different. That is based on the different experience of engineers, so there is nothing wrong if you are using some other book, but make sure you use some valid formula, not just assume it randomly, because if you assume it randomly, there will be obviously instability, the retaining wall will not come out to be stable. So keep that in mind to keep your values between these ranges. Obviously sometimes it may happen that if you are keeping all these values in these ranges, then also the retaining wall may fail, but there are chances for the stability also. Now next is length of toe slab. So this is the whole width which we have decided. So what will be the width of toe slab? That will be 0.3 to 0.4 of B. That is the B which we have decided here. 30 to 40% of that will be the width of your toe slab. Now thickness of base slab, that is this D of slab. I am writing here D because thickness is actually the depth which we have used earlier. That is, when we use beam etc., we always calculate depth. Here the depth means the thickness. Here also the depth means the thickness. So D slab will be 1/10 to 1/15 of the total height of retaining wall, but it should not be less than 300 mm in any case. Now what we are left with, thickness of stem. As you can see, the stem is slightly tapered. Here thickness is something else, here it is something else. I'll be explaining why this is done, but here we will look how we calculate this. The depth of the stem or the thickness of stem at the bottom is not assumed, but it is decided on the basis of maximum cantilever moment acting at base of stem. So what we do is, the stem behaves like a cantilever, and the load acting on this is the lateral force. So due to this lateral force, we calculate the moment here, because as it is cantilever, the maximum moment will be here. From that moment we calculate the D required, that is the effective D, and then we calculate the total D, which is the total depth. So the thickness of stem we do not assume, but we calculate on the basis of the maximum cantilever moment at base. Thickness of top is not calculated, but it is provided minimum as 150 mm, and it depends on how much you are calculating. You have calculated the thickness at the bottom. So why are we providing the stem as tapered, that is different thicknesses at top and bottom? This is because it is a very general concept. If this is your cantilever and here the load is acting, then the maximum moment will be here at the fixed end. So if you note the moment diagram of this, if you calculate the moment diagram, the maximum moment will be here, and up to here the moment will be 0, because as this is a cantilever, it is a free end. At free end the moment is 0, and here the moment is maximum, that is M. So we know that D is directly proportional to M, that is thickness is directly proportional to moment. So more moment will lead to more thickness, hence more thickness is required here. But 0 moment does not require much thickness, so for economy we reduce the thickness here. So I hope it is clear to you, as thickness or depth depends upon the value of bending moment, hence less thickness is required at top because of 0 or negligible moment at top. Therefore, for economic design of retaining wall, more thickness is provided at bottom and less is at top, because more thickness is not required at top due to the 0 moments. We have decided all the dimensions of the retaining wall components in step 3. We draw a diagram of retaining wall showing all the decided dimensions here in this diagram. So now your question changes to the one which we studied in the previous lecture, that is of stability analysis, in which you were given a retaining wall with given dimensions and given soil parameters, and you had to check whether that retaining wall is stable or not. So as you have decided all these dimensions on the basis of certain assumptions, so it's a law or rule of science that whenever you do anything, you do any assumption, you have to check whether it is correct or not. So you need to check whether due to these dimensions your retaining wall will come out to be stable or not. So that we will do with the help of stability analysis, which I already explained to you in detail earlier. Here we will calculate all the forces acting on this retaining wall, then we will calculate the moments due to these forces, and from after that we will be calculating the factor of safety of overturnings and sliding and for the failure of undersoil. If those factor of safety come out to be more than what is actually required as given in IS 456, then your retaining wall is safe. So when your retaining wall is safe, you can proceed to the next section. If any of the stability checks are failing, then it means that our assumption is not correct. So you may have to change any of the dimensions, or you may have to provide extra addition to the retaining wall, which case we will be studying later on in the problem. So I hope up to this point you are clear. You decide all the dimensions on the basis of assumption, and then you check its stability, and after that the stability checks are found to be okay. This means that your retaining wall is stable. Now you can provide the necessary reinforcement in the retaining wall components. So first we will start with the design of retaining wall stem. The design is very simple. You just need to know few basics of design. So for design, as I always say, first of all you need to know the structural behavior of that part. So I have repeated it many times. The cantilever behaves like a cantilever, and this is the tension phase. The stem behaves like a cantilever with tension phase here, and the load acting is this. What is this load? This is actually the lateral earth force acting on the retaining wall. So we will calculate, we will be having this force PAH. So first we calculate the earth pressure, and then we calculate the PAH. Why I am saying we calculate earth pressure earlier because if you are having certain saturated soil here, or if you are having soil with different layers here, the lateral earth pressure diagram will not exactly be like this. It may be different, as we have studied in the lecture number 2 of different earth pressure cases. So in any case, depending on the soil which is given to you, we calculate the value of PAH earlier. I have shown you how to calculate this value earlier. So this is the value, and where this is acting at this particular height. So what is this height? This height is actually the height of stem. This height is not the total height of the retaining wall. As we are dealing only with design of stem here, we will take this height to be small h here. So PAH into h by 3 will be the moment acting at base due to this particular force. So this is the base and this is the force, so the moment acting at this base will be PAH into h by 3. So when we solve this equation, we substitute the values of PAH. PAH is, for a basic simple case, PAH is area of this triangle half into base into height, that is half Ka gamma h into h. This is the value of PAH into h by 3. So that will give us m base equal to Ka gamma h cube 6. So I am repeating here that if the soil is saturated or having different layers, the value of m base will be slightly different, not exactly this. That will depend on you will have to calculate the value of PAH. Once we know the m base, that is the cantilever moment at the fixed end, then we can calculate the reinforcement also. So why are we only calculating the moment at fixed end? Because as you know from the basics of design of concrete structures, the reinforcement, whatever reinforcement you design, is for the maximum bending moment acting in that particular structural element. So in case of cantilever, the maximum bending moment is acting at the fixed end, and that value is the M base, which we calculated here. So now we know that as this is a cantilever and tension will be on the inner side due to this particular force. Therefore, where is the main reinforcement provided? The main reinforcement is always provided on the tension face. I have explained it here. Consider a cantilever acted upon by a transverse load, then it bends like this and the tension will come on the top face. Now our stem is also like this but inverted. Now this fixed ended here and this force is here like this. So the bending tension will come on this face like this. So I hope you understand why tension is coming on this face. So as if this was a cantilever beam, then the reinforcement would be provided along the length of your beam like this on the top face. Now in this case, as the direction of force is here and this is the tension face, so the reinforcement is provided along the length of your stem, that is along the height of the stem, due to the maximum bending moment acting on the stem, that is the base of stem. So if anyone asks you what is the main reinforcement in the stem of retaining wall, it is the vertical reinforcement acting on the inner side or the back side of your wall, not the front side, because this is the tension face and this is the compression face. So this is the main reinforcement and it is calculated from this formula. This formula you have studied a lot many times. Here M base is the maximum moment acting at the fixed end. From this you will calculate the value of AST, then you assume phi, that is diameter of main bar, and calculate the spacing. So if I will show you how this reinforcement will look. If this is the stem continuing in this direction, then this reinforcement will be provided vertically on the back side only. So this is very important, these two words, that is along the height of stem and on the back side. So this is the reinforcement due to the cantilever moment on the stem, and this is the spacing between these two reinforcement which we calculate here. So I hope this is clear to you. Now very important concept which you have studied before is the curtailment of enforcement. As I have mentioned to you earlier, this is a cantilever, so maximum moment will be at the base and it will continue towards the top. Like I will show you in this diagram. If this is the little earth force diagram, then maximum moment will be here and it will continue to decrease towards the top. So as we know that AST depends directly on the moment. So as moment increases, AST increases. As moment keeps on reducing towards top, the requirement of reinforcement will also be less. So it is better and it is obviously smart to reduce the reinforcement towards top, because the moment is reducing as we move upwards. So what we do, whenever moments reduce, we curtail the bars. So this is explained here. As moments keep on reducing towards top, hence reinforcement required also will reduce towards top, hence all the vertical bars may not be provided up to the top. So the vertical bars which we were providing from here to here, we will curtail some of them up to a particular height, so that in this bottom portion the AST is more and in the top portion the AST is less. So this is the curtailment of reinforcement. So how do we curtail reinforcement? I will show you in the numerical or the problem we discuss later. Main reinforcement consists of some vertical reinforcement along the height of retaining wall stem of full height, and some are of smaller or lesser heights. So we will discuss it later on, how these heights are decided on, at which level we have to curtail. Now Now we have calculated the main reinforcement, that is the vertical bars. These vertical bars need to be supported, as the retaining wall height can be up to 4 meter, 5 meter, 6 meter. Therefore, if vertical reinforcement bars are not supported with the help of some ties or lateral reinforcement, they may fail or they may buckle. So distribution reinforcement, which is the horizontal reinforcement, is provided across the height of the retaining wall stem like this, so that the vertical bars remain in position. How is this distribution reinforcement calculated? It is calculated by calculating the minimum reinforcement required in the stem of the retaining wall. So this is the inner face, back side of the stem of retaining wall. Here we have two types of reinforcement. One is the vertical bars. Some are of full height and some are of smaller heights, provided along the height of stem, which consists of the main reinforcement. And the second are these dots. This is the cross section and this is the L section. So these dots show the horizontal reinforcements which will be provided like this along the length of your stem in that direction. So these are those horizontal reinforcement, which is called as the distribution reinforcement. Now we have completed and provided the reinforcement on the inner face of the wall. Now what about the front face? As we know, this is the compression side. There will be no or very less movements in this side, so no reinforcement is required according to theoretical considerations. But as we are doing the design, limit state method design, so we always have to take the worst cases in picture, and we have to be safe at all times. So in order to be very safe, we provide certain amount of reinforcement on the front side also, although it is not required theoretically. So minimum amount of reinforcement is provided in inclined, or if your cantilever wall stem is like this, that is vertical on both sides, then this reinforcement will be also vertical. Here I have written inclined because this face is inclined. So minimum amount of reinforcement is also provided in inclined as well as horizontal direction on the front face. So this is the inclined reinforcement provided along the height of the stem, and these are the horizontal reinforcements, and these are calculated as the minimum amount of reinforcement. So we have four types of reinforcement in stem: main reinforcement on inner side, horizontal reinforcement on inner side, the distribution or temperature reinforcement, that is the inclined as well as the horizontal reinforcement on the front side or the outer side. So this is the design of your stem. Now next is the design of heel slab. So heel slab is this is the stem, which is this is its connection with the stem, which is fixed end BC. So what are the load which are leading to the cantilever action? This is the weight of backfill, and this is the upward soil pressure acting on the base of the retaining wall. So weight of backfill, downward direction, this soil pressure at fixed end of heel. So here don't look on this side, consider only heel slab portion. So we are looking at only the heel slab. So there are one load is this and one load is this. So this is the total load acting on the upward direction on the bottom face of your base slab. So as it is visible to you, this is a trapezoidal load with soil pressure. This is the soil pressure at the fixed end, and this is the soil pressure at the free end. We already have calculated these two values from before, and where we have done that while we were doing the stability analysis when we checked the condition for failure of undersoil, we had to calculate P maximum and P minimum. So this is your cantilever. Consider it as a cantilever beam with fixed end at B and free end at E. Now this is the load, upward load acting here, and this is the upward load acting here. This leads to a trapezoidal load like this. So we don't know this value yet, that is the fixed at the fixed end B. So how you will calculate it? From the basic law of interpolation. If you have this value, known value, and this known value and known distance between them, and if you have to find a value at this value x at any known location in between these two, it can be calculated easily with the help of interpolation. So we will calculate the pressure at fixed end of heel slab. So now our cantilever is subjected to two types of loads, that is, one is UDL, acting due to weight of soil, and second is the soil pressure, which is the trapezoidal load from below. So using the equation of equilibrium, sigma m is equal to 0, sigma m is equal to 0, we calculate the moment at B, which is the maximum moment due to the cantilever action due to this force and this force. So now that we have got MBC, we will use it to check whether the depth of slab which we have assumed previously in step number 3 is correct or not. So what we do, we calculate the depth required for this moment. So what does this mean? That for resisting this moment MBC, the minimum depth required for the base slab should be under root of MBC upon RB, and your this value you have already assumed before. So this value D slab, which we assumed in step number 3, should always be more than the D required. This is the minimum depth required below the base slab. So if in any case this checks comes out to be wrong, now you will have to revise this depth value here. You will have to increase this depth if this check comes out to be wrong. So now we have calculated MBC and the check for depth is done. We will now provide the main reinforcement in this cantilever, and that will be on the top face, because this is a heel slab in which this load will be always greater than this load. So the net force will be downward, and due to downward load the cantilever action will lead to tension on the upper face. So we will provide the reinforcement as main reinforcement along the width of your heel slab here for the maximum bending moment MBC at the cantilever end, provided along the width of heel slab at the top face like this, and this is calculated, AST is calculated using this equation. Now we calculate AST and assume die of bar and calculate the spacing. So this reinforcement will look like this. If this is the slab, heel slab in this direction, this was your stem in this direction, this is your retaining wall. So this is the main reinforcement provided along the this is the main reinforcement provided along the length of your heel slab. Now this we will provide at a particular spacing along the length of your across the length of your heel slab. So this spacing you will calculate here. Now, as we did in the case of stem, this main reinforcement has to be supported with the help of reinforcement in the opposite perpendicular direction, which is the distribution reinforcement. So distribution reinforcement in the heel slab is provided in perpendicular direction of the main reinforcement along the length of base slab at the top face like this. So your cross section will look like it. This is the main reinforcement, and these dots show the distribution reinforcement provided on the top face in the perpendicular direction of the main reinforcement like shown here. So this is the design for the top face of heel slab. Similarly, as done in the case of stem, the top face was under top face was under tension, so we provided the main reinforcement here. The bottom portion is under compression, where reinforcement is not required theoretically, but for safety we provide a minimum amount of reinforcement here also, along the width as well along the length at the bottom face also. So the cross section of your slab will look like this. These are the dots. So there are 4 types of reinforcement here also. Main reinforcement on top face along width of slab, distribution reinforcement on top face along the length of slab in that direction. Next is the minimum reinforcement at the bottom face in both the directions, that is along the length, along the width and along the length. So this is the design for heel slab. The design for toe slab will be same as that of heel slab, with a minor difference that here you will look at this particular portion only, as this is the fixed end. So now this is the upward force acting on your heel slab, and the downward force due to weight of this soil has been neglected. So there will be only 2 forces, only one force actually. This is 1 P maximum, and this is the soil pressure at your fixed end AD. So this is a trapezoidal load. This also we will calculate by linear interpolation. We know both these value, and we know that this total distance we have to calculate at this particular point, so we can find out this force X. So when we get these 2 forces, this comes out to be a trapezoidal load. We calculate the moment MAD by summation M is equal to 0, and we get the maximum moment at the toe slab at the fixed end MAD. Here the behavior will be totally different, opposite, because this is the upward force now, so this will be the tension phase, the bottom portion. So here reinforcement is provided like this. So for the maximum bending moment MAD, we calculate the reinforcement using this formula, and this reinforcement is provided at the bottom face, main reinforcement, and this is the distribution reinforcement provided in this direction at the bottom face, which is the minimum reinforcement. Similarly, in the compression side also, for safety we provide minimum reinforcement in this as well as in this direction. So the toe slab is exactly like heel slab, but with a difference in the reversal in the direction of load, leading to reversal in the position of tension phase. So this concludes your design. So in this diagram I have shown you all the various types of reinforcements. So let us summarize. Starting from the stem, we have vertical reinforcement. This vertical reinforcement must be extended to your base slab for proper bondage of both these junctions, for both these components. So this is the reinforcement along full height, and these are the curtailments. These curtailments have been provided at 2 heights to save more reinforcement. You can see the longitudinal section of stem. This is full height reinforcement, this is smaller height, and this is smaller height. So 3 lengths of reinforcements are provided. These dots show the distribution reinforcement on the inner side of your stem. This is the reinforcement on the compression side, that is the outer side, in inclined and horizontal direction. Now we have the reinforcement in heel slab. Main reinforcement is this, and in toe slab main reinforcement is this at bottom face. All these other reinforcements are the distribution reinforcement on top slab, top face and the bottom face, and here distribution reinforcement on the top face. So I hope the detailing of whole retaining wall is clear to you. Now we will look at this diagram I have downloaded from internet. That this diagram is showing all the reinforcements which I showed to you in the previous slide. Here you can see in the L section or elevation of wall, you can see one reinforcement of full height, next of smaller height, then full height, smaller height, etc. Alternatively in the this direction. These red bars show the horizontal distribution reinforcement along the height of across the height of wall, which has been provided to support this vertical reinforcement. These black dots and this black line are the distribution reinforcement in the compression phase, and this blue line and this pink line are showing the main reinforcement in your top face of heel slab and bottom face of your toe slab, and red dots are showing their respective distribution reinforcement. Here this portion has been left blank without any reinforcement, but you may extend certain amount of reinforcement here for safety, or provide additional reinforcement here also for safety. So this was all about the design and detailing of your cantilever retaining wall. Now we will go through a design problem quickly. So here we have been given a cantilever retaining wall which has to retain a backfill of 4 meter height above the ground surface with soil properties gamma, phi and soil bearing capacity as given in the question. Coefficient of friction is also given, and the grade of steel and concrete to be used are also specified. So we will do this question exactly as the steps which I explained to you earlier. So first we have been given the soil parameters of this backfill and this soil, and if not given separately, assume that both these soil parameters are same. The height of the backfill above the ground level has been given as 4 meter. So first step is calculation of the depth of the base slab or foundation below the ground surface, which is this formula. Here Q is 180, gamma is 18, phi is 30 degree. So we calculate all these parameters to get H minimum as 1.2. Therefore total height of retaining wall, this comes out to be 4 plus 1.2, that is 5.2 meter. Now we have got the total height of retaining wall. We have also calculated Ka here, here only because we will be using it later. Ka is the coefficient of active earth pressure. As nothing is specified about the inclined backfill or about the saturated soil etc., so we will assume that this is having horizontal backfill with same type of soil, dry soil here. So Ka, for that case, Ka is 1 minus sin phi upon 1 plus sin phi. We get Ka as 1 by 3. Now the third step is the preliminary dimensioning. Base width is 0.4h to 0.6h. So here we get 2.1 meter to 3.2 meter. H is 5.2 meter. We calculate this range and assume any value in between that. Similarly, we calculate length of toe slab, base slab thickness h by 10. Now thickness of stem at base, as I mentioned earlier, we do not assume it but calculate it by considering cantilever bending moment. So pressure at stem base is Ka into gamma h. Here gamma h here h is the height of your stem, this. So the height of your backfill above ground level was 4 meter, and this you have assumed to be, this is the thickness of base slab you have assumed to be 0.5 meter, and this total height was 5.2 meter. So we have to calculate the height of stem only, that will be 5.2 minus 0.5 meter, which is 4.7 meter. That's why we get here 4.7. Ka is 1 by 3, gamma is 18. So this pressure here we get as Ka gamma h. Now Pa will be area of this triangle, half of height into base. So we get Pa from this formula, and then we calculate the moment acting at the base of this stem due to this force, which is Pa into h by 3. This h by 3, which we get as 103.83 kilonewton meter. This I have already explained earlier to you. Now this is moment 103.83. We multiply it with 1.5 to get the design bending moment 155. So on the basis of this design moment, we calculate the minimum thickness of stem required at this point of maximum bending. So or depth of stem required will be d is equal to under root m upon rb, like this, and we get d as 238 mm. We assume cover to be of 60 mm and calculate the capital D of your that is the thickness of your stem at the base, 350 mm. Now as we all know that the maximum bending moment is as fixed end, so here we have defined or decided the thickness to be 350. The bending moment goes reducing towards top, so we don't require this much thickness here because this will lead to uneconomic section and the concrete will be wasted here. So we reduce this thickness to a smaller value, which is minimum taken as 150 mm. You can also take it to be 200 mm, it is up to you, but we try to keep it as minimum as possible because here we have zero moment. So now we have decided all the dimensions of the retaining wall, its height, its the width of your base slab, width of toe slab, thickness of stem at top, at base, all these, and thickness of base slab, all these things have been decided. So now what is the next step? We have to check whether the assumptions are correct or not. So for that we will do the stability analysis. I will not explain this portion to you again. I will just explain to you one point here which is important. Rest you will do it yourself because I have already covered in detail in the previous lecture. So the first step is to calculate all types of forces. So what are the different types of forces? The main force is this pressure. So when you calculate this force, always keep in mind take this total height h, which is 5.2 meter. In the previous step, when we were calculating the moment at the base of stem, we took the height as only this much up to this point because we were considering only the stem. So we calculated the force or pressure acting at the stem base, not the base of retaining wall. But now we are calculating the lateral earth pressure on whole of this retaining wall because we have to calculate the moments due to this. So here we will take the full height, that is 5.2. So keep this difference in mind. So now we calculate PA, its lever arm, and calculate the overturning moment. Then we calculate all the different weights acting on this retaining wall, and we calculate the restoring moment, the summation of vertical forces and summation of horizontal forces. Then we apply all the stability checks. This also I will not explain, just look here that the overturning factor of safety is coming out to be 2.2, which is greater than 1.4, hence safe. The sliding factor of safety is coming out to be 0.99, which is less than 1.4, hence not safe. This type of problem, which this also we did in the previous question. So when the sliding factor of safety is coming out to be less, you don't need to revise your dimensions, you just need to add another component to your retaining wall, that is the shear key. Shear key design has also been explained to you in the previous lecture. So remember this, at the end of this question we will have to decide the shear key also, its dimensions. Now the third is the base pressure or the under soil. Here we calculate P maximum and P minimum, and this value should be less than the soil bearing capacity, and P minimum should be positive, hence safe. So one check has failed. For that we have the solution of shear key, rest of the checks are fine. So now we can proceed with our question. So we will provide the reinforcements in different portions. First is the design of stem. For stem, what we do, we calculate the moment acting at the base of stem, which is the maximum moment due to this force, and for this moment we calculate the reinforcement. This we have already calculated by we were deciding the thickness of the base stem, so you don't need to repeat it. So so directly I will take it as 155. For that you will calculate the reinforcement required, which is coming out to be 1693. we assume the diameter of bar and calculate the spacing. So we have concluded that we have to provide 16 mm dia bars at 100 mm spacing of 100 mm center to center as the main reinforcement on the inner face of stem towards the backfill. So this is the vertical reinforcement. So as I have explained to you before also, this reinforcement is due to this maximum bending moment at the base. But as we know, we do not require too much reinforcement at the top portion because here bending moment will be quite less as compared to this value. Therefore, the reinforcement will also come out to be quite less. So we have to curtail the bars. So what we need actually, we need to have, if this is the wall or the stem, we need to have denser reinforcement in bottom portion due to more moments and less denser or spacious reinforcement at the top portion due to reducing moment. So we will have to curtail once or twice depending on the length or height of your stem. So we have to calculate that the length or height at which we have to curtail the reinforcement. So I will go to the curtailment part here. So as stem behaves like a cantilever, bending moment reduces towards the top, therefore main reinforcement is not required near the top. So first curtailment, that is the first height. If this is the full height of reinforcement bar, then the second bar has to be curtailed at a particular height. So we have to calculate this particular height. So we know from the limit state of bond concept that we have to calculate, we have to cut this bar at least, or we have to provide that much length of height of reinforcement so that it covers the limit state of bond condition and it gives the required development length. So we will provide the first cut at the minimum required development length of bar. So you know this formula very well. It is the development length required for this bar, so we calculate it to be 752 mm. So this means that a minimum height of 752 mm should be required for any bar of diameter 16 mm provided here. But we can round it off, and also for limit state of bond we can increase it height more, so that more length will lead to more bond and proper dispersal of forces. So curtail bars at 1000 mm from base of stem. So now we have to curtail this bar here. So what we will do, we have provided this curtailment here at 1 meter height. So what will be the spacing here that we have to decide here. For that you will need to find out the moment acting at this point. So I will erase again and draw again. So this was your stem. This was the total height of vertical bar required. This was due to the moment acting at this height, that is the moment acting at height 4.7 meters. Now we need to calculate the moment at this height, which is, this is 1 meter. So what will be, as you know, when we are calculating the moment, we need this height, not this height. Okay, so we need to calculate this distance from top. So if this is 1 meter and this is totally 4.7 meter, this height will come out to be 3.7 meter. So now our earth pressure will act here, and earth pressure at this point will come out to be half Ka gamma h, where h will be 3.7, not 4.7. So we calculate the moment at this point, which is coming out to be 50, and the moment at this point was 150. So you can see in 1 meter height the moment is dropping so much. So 150 and 150 and 50 are have great difference. So mu is 76. If you multiply it by 1.5, calculating the design moment. So the AST required is 924. Using the same 16 mm dia bars, we calculate the spacing 200 mm. So in the first case here, when we are taking the total moment at base, we need 16 mm dia bars at 100 mm center to center near the bottom portion, and at this height where we have put the curtailment, that is 1 meter, we don't need this much reinforcement. We need 16 mm dia bars at 200 mm center to center. So it is clear to you that half of the reinforcement can be curtailed at this particular height. Similarly, we can do another curtailment also at a larger height, that is, for example, here. This you can do at any point wherever you require. Here we have taken it to be at 1.5 meter from top of stem. From here 1.5 meter, we do the same thing, and we calculate the moment at this particular point, and we calculate the AST and provide the reinforcement here. So we have done two curtailments here. First at this height at 1.3 meter from base, and second is at 1.5 meter from top. Note here, this is 1.5 meter from top, and here it is 1.3 meter from base. So what we will get is, this is the full height of bar, this is one curtailment, and this is the second curtailment. So this was the 1 meter height, this was the second curtailment, which was the distance of 1.5 meter from top. So you can calculate 4.7 minus 1.5 at this height, and the third bar you have provided at full height. So as you can see here clearly, if we repeat it alternatively, in this portion, that is in this portion, it is the lowermost portion of your cantilever wall, we are getting dense reinforcement with less spacing, which is 100 mm. In this portion, which is the second layer of your reinforcement, here we are getting more spacing as compared to here. So this will come out to be double, that is 200. And in the topmost portion where the moments are very less, here we get the reinforcement as 400 mm center to center. So you can see how easily we can curtail the reinforcement and how easily we are saving so much material of reinforcement. You don't need to do so much calculations every time. With practice and with time, you will learn how to do this curtailment swiftly and quickly. So the main now this is the main reinforcement on the top face, on the inner side of your stem. Now next is the distribution reinforcement. The distribution reinforcement is the horizontal bars which are provided along the height of your across the height of your stem to support these vertical reinforcement. And how are these calculated? This is the minimum amount of reinforcement, which is 0.12% of cross sectional area. The cross sectional area of stem will be B into D, where B is the width 1000, as B will be taking in this direction 1 meter length, and D will be the depth of stem. So as we know, the stem is varying with height. We take the mean depth, which is 150 at top, 350 at bottom, divided by 2, and calculate the AST and the spacing required. So we get 8 mm dia bars at 150 mm center to center on the inner face of stem as distribution horizontal steel. Similarly, on the compression side also we get the same amount of reinforcement. You can also change the diameter of bar accordingly as you wish. So now we have got 4 types of reinforcement: vertical bar on inner side, horizontal bar on inner side, vertical and horizontal bars on outer side of the retaining wall stem. So I have summarized this in this table, In the back face of wall or in the tension phase, we have main reinforcement, vertical reinforcement on back side of height 1.3 meter from base, which have been curtailed, which I have designated as A in the detailing later on, and the reinforcement was this. The second curtailment was made at 3.2 meter from base, and this is this much. And the third, this is the first curtailment, this is the second curtailment, and this is the third vertical bar provided along the full height of your stem, in where the reinforcement is less, that is at much larger spacing. Now this was the tension phase, and in tension phase we have another distribution reinforcement in horizontal direction designated by B, and this is 8 mm dia bar at 150 center to center. In the compression phase we have temperature or distribution reinforcement in vertical as well as horizontal phase, same 8 mm dia bar at 150 mm center to center. So this is the summary of this stem. A was the reinforcement for the maximum moment up to this much height. A1 was the reinforcement curtailment here, and the total reinforcement was A2 at the full height of the retaining wall or the stem of retaining wall. B was the distribution reinforcement in the inner face. C was the distribution reinforcement in the front face in inclined as well as horizontal direction. So as you can see here, we have provided 3 types of curtailments. Now we will do the design of heel slab. So first of all we will calculate the loads. So this is the weight of soil, height of soil into gamma, and P minimum and P maximum we have already calculated earlier. Now heel slab acts as a cantilever supported on the face CF here. We will now have to calculate this value of pressure here. So the loads acting on heel slab are weight of earth on heel 18 into 4.7. Self weight of heel slab will also be act in addition to this. This will also act in the vertical downward direction. So as we know the dimension of this and this, we will calculate this to be 12.5. Note that I have calculated all these values in kilonewton per meter. So we get the total downward load as 97.1. Now we have to find out this value at CF. So this is clearly from interpolation. Here the P maximum is 124, P minimum is 17.83. Distance between these two is 2.8 meter, as this is the whole base slab width. We have to calculate here the pressure. The position of this point is 1.6 meter from here. So we will use the interpolation formula. This value will be bigger than 17.83 and lesser than 124.83. So pressure will be 17.83 plus some value. So what is this value? Here we are using unitary method. From this variation, for a variation of 17.83 to 124.83 in 2.8 meter length, if we have a variation of 124.83 minus 17.83 in the length 2.8 meters, then what will be the variation in the length 1.6 meter? That will be this. This is basically unitary method. So I hope you will understand this. So PCF is 78.4. So now this value we have 78.4, this 97.1, and this is 17.83. This is a trapezoidal load. So we calculate the moment at CF. So we use the formula sigma m at C is equal to 0. So for moment due to this UDL at this point will be 97.1 into centroid of this UDL, that is 1.6 into 1.6 by 2. 1.6 by 2 is the lever arm of this particular force. Now when we do trapezoidal load, we divide this load into 2 diagrams, that is one rectangular load and one is the triangular load. So if this is your trapezoidal load, if this value is 17, then this will also be 17, and this will be here total value 78, so this will be 78 minus 17. So now we have two types of loads here. This is the rectangular load 17.83 kilonewton per meter acting on length 1.6 meter, and its lever arm will be 1.6 by 2, and second is triangular load of value half into base, that is 1.6, the height which is 78.4 minus 17.83. this is the total UVL, that is triangular load, into the lever arm. The lever arm will be the centroid of this triangle, which is 1.6 divided by 3. So solving this, we get the value of moment at CF to be 75.7 kilonewton meter, and we multiply it by 1.5 to get the design value. So the value, maximum bending moment value at the fixed end of heel slab is 113.6. We check the D required, which is coming out to be 202, and compare it with the D provided. The D provided here was 0.5 meter, which we had assumed in step number 3, and the D required is 202, hence our assumption is correct. Now the reinforcement is provided due to this moment 113.5, which we got from here, and 113.6, and we calculate the AST and the spacing required. So this will be, if this is the heel slab, this reinforcement will be provided on the top face due to the downward direction of load along the length of your slab like this, along the width of your heel slab like this, but at the spacing of 150 mm center to center on the top face. Similarly, distribution reinforcement is provided here, which is equal to the minimum reinforcement 0.12% of B into D, which is 0.5 meter. So here we calculate the spacing, which is coming out to be 100. So here I have taken a lesser diameter bar, 10 mm dia bar, and spacing is coming out to be 100 mm. Similarly, we can calculate the bottom reinforcement also. It has not been calculated here, but you can calculate. It will come out to be same if you take the same diameter, 10 mm dia bar at 100 mm center to center in both directions, this as well as this. Now similarly, the design of toe slab is also done like I explained in the heel slab. We calculate the force or the upward force acting at BG, and then we calculate the maximum moment acting at BG for this trapezoidal load, it has been split into two portions, that is this rectangular one and this triangular one, and we get the value of mu, which is 61.8. For this we calculate AST, which is coming out to be less than AST minimum. AST minimum I have already calculated while we were calculating the distribution bars. So as AST required is coming out to be less than AST minimum, we will provide the AST minimum. You know this rule. So the reinforcement in the main reinforcement will be also minimum reinforcement. So in the toe slab we provide main reinforcement as like this, if this is the toe slab and this is the stem here. So the main reinforcement is provided in the bottom face now, as the direction of load is this. So it is provided along the width of your toe slab, and the distribution reinforcement is provided like this, and these all are minimum reinforcement 10 mm at 100 mm center to center. So this is the design of heel slab and toe slab. I have tabulated these all in this particular table. You can see it later on. I will give you the this presentation also. So here we get whole detailing. Here D is the main reinforcement in your heel slab. Main reinforcement in heel slab is D, 12 mm dia bar at 150. E is the distribution reinforcement on the top face of your heel slab. F is the main reinforcement in toe slab, and G is the distribution reinforcement in toe slab. Rest all these are the extra reinforcement which have been provided, which are basically these are extended up to here so that for better safety. Now that we are done with all the components, we will design the shear key as the stability check was sliding has failed. So I will not explain it again, I have explained it to you in the previous video. We just assume a shear key of depth A and calculate the passive earth force acting due to this soil here present on the front face of your wall. This is the front ground surface of your wall, so there will be passive earth pressure acting on this. We consider only the shear key portion because we are concerned about here only, so we calculate pressure at here and at this point. We add it to the restoring force. Restoring force is the mu times of summation of V, that is the frictional force plus resistance offered by shear key, which we get as 277 into A. Now the sliding factor should be greater than or equal to 1.4, so we substitute all these values and we get the value of A as 118 mm, so we provide it to be 200 mm on a safer side. So this is the design of shear key. You can refer the previous presentation for a better understanding of how we got this value. Here some assumptions and some values have been taken in a simpler way, but you can do it on the method as I explained in the previous slide. So this was the design of your cantilever retaining wall. Now this is the whole detailing of your retaining wall. Let us start from the stem. We have curtailed vertical bars here. Some are of full height, some are of 1.3 meter height, and some are of 1.5 meter at 1.5 meter from top. So the three types of lengths of vertical bars are in the stem: this, and this. These are at spacing of 100 mm. So this is the bottom area in which we require most of the reinforcement. Then second phase, spacing 200 mm, and third phase where movements will be very less. You can see we have provided very less amount of reinforcement. So see how much material of reinforcement and cost of reinforcement you are saving here. So this is the main reinforcement of your stem, which has been shown in this cross section also. So whenever you are drawing the detailing, you have to draw the cross section as well as the L section of the retaining wall. So here you can see this vertical line, and this and this hook are showing the curtailed bars. Now these are 16 mm dia at 100 mm center to center, at 200 and at 400. This is the distribution reinforcement in the inner side, which is I think 8 mm at 150 mm center to center. When you are doing this particular detailing, you can open the table which I have summarized in the previous slide. You can cross check with that. So this is the tension phase of your stem. Now in the compression phase, we have both bars of same value, that is, I think I have not written here, but it was same 8 mm dia bars at 150 mm center to center. Yeah, here 8 mm dia at 150 mm center to center. So this was the stem. The reinforcement of stem has been extended to the base slab for better junction. Now in the base slab, the main reinforcement is top of heel slab and bottom of the toe slab, and these are the distribution bars, and this is the compression side of heel slab and toe slab. So here you have to provide the minimum reinforcement. So this is the complete detailing of your stem. So I hope you have understood this particular topic. You can practice more and more questions on cantilever retaining walls for better understanding. Now we will be studying first the steps for design of retaining wall, and then we will be solving a problem of the same. So whenever you have to decide a retaining wall, the one thing which has to be given to you and which you must know before is the height of the backfill which you have to retain, or which the retaining wall have to retain, and the properties of the soil which we have to retain. So these two are very important things, that is the height which you have to retain and height of backfill, and the backfill soil properties. Without this you cannot do the design of retaining wall. If you will have to assume certain things if this data is not given. So height of backfill is the slope which you have to retain, which is according to the site condition. So retaining wall is designed as follows. So we will be covering it step by step. So first step is the location of the base slab below the ground level. As I have told to you earlier also, your retaining wall is generally not directly at the ground level. Here it is slightly below the ground level. This is for the safety of the base slab and for the retaining wall hole. So we have studied this formula while we designed foundations, that is the minimum depth of slab of retaining wall or foundation below the ground level. How deep the foundation or the base slab of retaining wall should be provided below the ground level for safety. So we use this formula. H minimum is 1 minus sin phi upon 1 plus sin phi whole square into Q naught into gamma, where phi is the angle of friction or angle of repose of this soil, Q naught is the is the bearing capacity of this soil, and gamma is the density of this soil. So if you know all this, you can calculate the H minimum, that is the minimum depth of foundation or minimum depth of base slab which is required. Why are we calculating this value? Because you have been given the height of backfill, that is, if this is the backfill, this is the slope that you have. For example, this is the slope which you have to retain, this is the portion which you have to retain. So this much height you will be given, height h, let us call it small h. So but as we know, I said here also, the retaining wall is not of this height but some more height below the ground level also. So the total height calculation requires both these values, h and h minimum. So once you decide h minimum, you can calculate the total height of the retaining wall. So now consequently the next step will be total height of retaining wall, which is h plus h minimum. Sorry, this is not h minimum. I think this diagram is incorrect. I will redraw it. If this is your retaining wall and this is the ground level, you will be given this height, that is height of backfill from the ground surface, and this is h minimum. So kindly correct this diagram. These values are from here to here, and below that is h minimum. So this will give you the total height of retaining wall which you have to decide. Now third step is the most important step, that is preliminary dimensioning of retaining wall components. So when we designed beam or column, we used to assume one of the things, like in case of beams we used to assume the width of the beam and we used to calculate the depth of the beam. Similarly here also we will do the same thing. Some of the assumptions, we are doing some of the assumptions more here as compared to beams because there are a lot of components here. So according for this, certain rules have been defined, or not rules, but according to the past research and according to the experience of engineers, some basic formulas have been devised that range of your different dimensions for the safety of retaining wall. Like first is for dimensioning of retaining wall, what you have to do, you have to decide